So last time I mostly talked about the technical side. I know the process is painful. If you haven't prepared, you probably don't know much about what I'm talking about. You couldn't follow too much. I was mostly referring to the implementation steps and details, and didn't talk too much about intuition, didn't talk too much about rationale, mostly the steps, right? But some little bit of familiarity with how the process look like is important for me to talk about intuitions. Otherwise, intuition won't make sense. You won't be able to connect intuition with the steps or with the cycle, the process. So that's why. And I'm gonna spend a little bit time today to overview what the steps really mean for about the Adeline model. If you have started doing the homework, you will start to be able to connect the dots. Even if the homework is straightforward to you, yeah, Adeline model is quite straightforward. If you know the basics of Python, and if you have a basic understanding of the Adeline model, the critical steps I talked about last week, you would be able to fairly understand them. With intuitions explained, you would have a better sort of at the interpretation level, you would sort of be able to explain to other people what this is doing, what that is doing. Connecting the technical steps to how the model is really learning, and what is this step doing in the entire process? What is the effect of this step on the learning process of the model? That's what I'm going to focus on first. I'll spend about 15-20 minutes on that. Then, clear any remaining questions in terms of confusion, understanding. Then we'll move on to logistic regression. Yeah. So let me share my screen and the slides. Can you all see it?
Yes.
Yeah. Okay, let's move this down.
Can I give you my interpretation of Adeline model? See if that's correct, or should I wait after class?
Yeah. Well, if it's not long, go ahead.
It's not long. So there's multiple inputs that have an arbitrary weight attached to it. You run it through the black box algorithm, and you compare the results to the actual results. And then when you compare it, you update the weight, and then you run it through the loop until you get to the threshold. And after it meets the threshold requirement, it goes to the output, something like that.
Are you describing one loop, or are you describing the entire training process?
I would say one loop.
Okay, that's great. That's fairly reasonable. One thing I would correct or encourage to think otherwise is that it's no longer a black box anymore. You are actually seeing what's happening inside. You're calculating the steps you're calculating the process step by step. So now the black box is opened. It's not black box anymore. I hope that's crystal clear.
Got it.
Okay. So that's the purpose of this course. Is after this course, you are not only seeing a black box, you should be able to explain what the black box is doing, for other people who can't see. Now you have a view inside, and you can diagnose what's going on if there's any problem. Fair? Great.
Got it.
Right. So I've made this process, and this is not in your slides. And hold on. And I hope to illustrate that process and convey that to you. Okay, so Adeline model overview. This is, using an alternative set of symbols and also languages to explain what's happening. All right. Let me change my laser point. Oh, this doesn't work well. Let me do this. Something is responding very slow. Oh, this may work. Let's see. So, Adeline model. You can think of that somewhat similar to a neural network model, but there is no hidden layer. So there are only two layers, the input layer and the output layer. And for Adeline model, as well as logistic regression, the output layer will always have one node. So basically, you have one node on the end, on the right end, which is the end of the flow, right? Imagine one node. I'll display them in a second. That's the output layer. In the input layer, there are multiple variables, multiple inputs. I like to use J to index the input variable X. Now, there are many dimensions. Let's use M to refer to the number of columns in the pre-processed input data set, which is the X data set. The number of columns will correspond to the number of features or number of attributes or number of variables, what have you, different terms to refer to the same thing, right? And there's an additional bias term, which is sort of like part of the input data, but it's always going to be one. It's similar to the intercept term of the linear regression model. So that's it. With the simple setup, the first step, if you recall, you can take out the process cheat sheet, which is always helpful. It's shown. It's highlighted here. This is Adeline in the process model. I'll basically talk about these in the order, but in the context of the flow. Right, the flow goes clockwise. One loop is the one loop of the epoch. Although the input variable will not go through the loop for every time. It will only go through. It will only enter in the first loop. So that's kind of not part of the loop, but for illustration purposes, this is fine. For every input variable, you have a corresponding coefficient that we call weight, right? So if there are m number of columns in the x variable, x input data set, there should be m number of weights associated with each. Plus, there is a bias. The bias is associated with the one term, which is always one. So the bias term stand on itself is added to the net input. So this notation shows that for all the input, the value of the input variable should be multiplied by the corresponding weight, so that the weight is modifying what the input variable is affecting the net weight, the net input. By adjusting the weights, you can adjust the effect or the impact that each of the variable is making on the ultimate prediction or the output. So your objective is to properly optimize these weights so that the model can predict in a better sense. With this notation, it's fairly straightforward to think of the first step, which is the sigma net input step. Now we use Z, I use Z to refer to the net input, right? And this sigma is simply weighted sum of the input variable for every row of the data set, right? Make sense? So you can imagine your mind, in your head, what is this doing? The formula would be the weighted sum is by multiplying each of the input with the corresponding weight and then calculate the sum. That is exactly what the formula will say. So what is this step doing? It's collecting inputs, but it's adding a weight. So that if the weights are optimized, ideally, the model would be, the weights are part of the model. What characterizes the model is essentially the combination of these different weights, right? By optimizing the model, you're optimizing the weights. So you're applying a set of weights, potentially different for every input variable, but not different for every row of the data. It should be the same for the same column, right? You multiply the weights to the corresponding input data so that some of these weights will emphasize some of the variables, but the other weights could be very close to zero, which means the model has recognized that those variables are not particularly helpful in predicting the outcome. So the model will adaptively minimize those weights to minimize the input, the effect of those input dimensions, which means that the variables, while emphasize the rest of the more informative inputs. That's what the weights do. Then if you put the weights together, it's a vector of length, not only m, but n plus 1. The plus 1 part is the bias. And we tend to put the bias in the beginning, which is easier to refer to. With index 0, it's always the bias. So with the net input, you weight the input with the weights and then calculate the sum. So that's a way to reduce the dimension, reduce the complexity of the input information while still be able to count everything. You want to include every bit of signal that comes in from the data, but then in a way to modify the signal to emphasize the useful signals, but to diminish those not very useful signals. That's what you're doing in the net input. But so far, the combination is still doing a linear combination, right? So what it means, even with optimized weights, you are only able to separate the points using a linear hyperplane in a hyperdimensional space. So with a linear hyperplane, you probably can only do this much. You cannot really effectively differentiate the different classes. So in this step, hopefully you have something to non-linearly discriminate different points with regard to their outcome so that you can apply the penalty more, distribute the penalty more clearly. That's what the activation does. However, the caveat with Adeline is that the activation does nothing. The caveat is it does nothing. It simply does a linear transformation. So still linear. So the drawback of Adeline is that you do not have the benefit of non-linear firing of the model. But logistic regression fixes this part, at least improves this part. And the real impact is what? So, the difference between Adeline and logistic regression is really only the activation function is different. And another small difference is how you calculate the cost. But that's not really a difference. That difference doesn't affect the training. The difference only affects how you can make use of the calculations of the logistic regression to sort of imitate the concept of probability. That's an added benefits of using Sigmoid function. But that's a different story. The real difference there is only that it changes from linear activation to a nonlinear activation with Sigmoid function. So what does this really do then in terms of training? You will notice later on today, hopefully today in demonstration, I will have time to talk about that. The real impact of that is with linear activation, which does nothing. Your optimization process becomes very sensitive to the values as a result of initially random draws. With random draws, random draws of weight coefficients, the model could be predicting poorly, right? Initially, it's a random model. You have to have some starting point, but the model is not good. With that, you have a big error. You have a big bias in the model. So the model is trying to optimize by using gradient, which I will talk about later, by using a gradient. But because of because model is poor, gradient is large because the mechanism is trying to correct the problem. It's trying to optimize the weights by leveraging the gradient as soon as possible, as quickly as possible. With a large gradient and with linear activation, the error is also large. If you recall, you probably don't recall, but because the steps are complex. But as a side note here, hold on. As a side note, the gradient is calculated as the gradient of these weights, which is associated with the output unit here, is calculated as that. E refers to error. When a model is poor and when the activation is linear, which doesn't smooth out, doesn't squeeze values into a small region, the error could be huge. When the error is huge, you get a very big gradient. When you have a very big gradient, if you don't have small enough ADA learning rate, your delta weight becomes huge. So in a way, you are not really improving the model, but you are degrading the model over and over. The cost function in the end, because of the increased error, cost function is basically sum of squared error, right? If the error is exploding, the cost function exploded. So that's why with a large ADA in the previous class, you see that the cost function is increasing exponentially rather than decreasing. So this is the drawback of the linear activation. You don't have the added benefits of smooth out or not smooth out, but squeezed, limited sort of error space. The error space can explode. With Sigmoid function, it kind of limits the error space to a limited area. So you don't have to have a very small ADA. You can have ADA that was originally chosen, which led to exploding cost function of the Adeline. But with logistic regression, you can use bigger ADA, and you need to use bigger ADA because you need to learn fast enough for the model. So that's what the linear activation really is doing as compared to Sigmoid function for Adeline model. But again, the framework of having the activation step, even though it does nothing, helps you better adapt to logistic regression later. So that's a side story here. Now, after the linear activation, which does nothing, it will pass the net input to the next step. So what is net input again? It's a linear but weighted combination of the input signal. So basically you have collected all the signal. The next step is to compare the signal, compare the net weight, which represents the total signal, compare that with the actual data to calculate the error. How far off your current prediction based on your current weights are doing. How far off is it from the ground truth? Then then you have a sense of the distance between the current model and the optimal model, right? That's the error. Error is something that you want to reduce, based on some kind of function of the error to summarize the total error of the data set, right? So the total error is then the cost. So what is the cost again? How is cost related to error? Cost or loss, same thing.
Positively correlated. You said when one goes up, the other goes up too.
Yes, directly associated, but we tend not to. We don't use coefficients to describe it here. I would let's see. I would insist that you need to know the mechanistic relationship. What is the cost? It's sum of squared error. That's it. Very simple, very straightforward, but very precise. It's sum of squared error. Clear cut. Sum of squared error of all the data points in the training set. So if error is greater, cost is greater. You are trying to minimize the cost in a way you're trying to minimize the error. Then if error is minimized, your prediction, which is here, it's the activated input. The activated input, the difference between activated input and the Y label is minimized. Then all your prediction is correct, right? That's your objective. So I hope that's crystal clear. That has to be clear. So cost, we typically use this function, and cost is a function of the weights. Because the weights are not optimal, that's a reason where you have errors. If the weights can be optimized, the model is optimized, and your predictions will be close enough or very close to the true label, and you won't have any error. So cost is a direct function of the weights, right? That's the only thing that you're trying to optimize. That's all. That's the only thing you're improving by learning, by having the model learn from the data. So far, makes sense? Nodding or shaking? Right, so, and so far, it's a forward prop. It's all moving this direction, it's forward prop. You may say, the error is not really a forward prop, but it's the transition between forward prop and back prop. You are preparing to calculate the gradient by calculating the error. So you're trying to send some feedback back to the starting point, which is the weights. But now you understand that how cost is related to the weights. Cost is a function of weights. So after calculating the error, you need to the model is trying to find a way to know how to improve the weights. So we will make use of the gradient. It's again this graph where imagine the cost is on the y-axis. Imagine the cost is a function is a function of only one input to simplify the interpretation here. Assume that we only have one variable, m equal 1. Then we can make this graph to see the relationship between the weight and the cost. And by a random draw, our model can be anywhere in this curve. But the objectives are clear. You're trying to get to the bottom of the cost. So you'll need to glide down the cost curve. And gliding down the cost curve, we can make use of the gradient, but to reverse the sign of the gradient of the curve, because we want to go down instead of go up, right? So that is plotting, visualizing the cost function as related to the weight. And it's in this process that we can use the gradient to improve the weight. We know how to adjust the weight by using the gradient. So that's why we calculate the gradient. This is the gradient, right? And after having the gradient, then there are two remaining simple steps. You will calculate the adjusted weight. And this step is very intuitive. Once you have the gradient, getting the actual weight update is rather an empirical question, because the weight update is simply a function of multiplying the ADA learning rate with the gradient and reverse the sign of the gradient, right? So what value of ADA should you choose? It's an empirical question. I said for Adeline model, you need a really small ADA because of a lack of nonlinear firing. But for logistic regression and further down the road, the neural networks, the learning rate doesn't have to be very small. And actually, there's a way to optimize the learning rate dynamics. Inside the training, you can dynamically change the learning rate in order to achieve optimal model learning process. And that is more advanced topic that we'll talk about in the neural networks. After you have the delta weight, that's one more simple step. Is simply to update the weight by adding the weight update to the original weight and feedback and replace the old weights with the new weights. Now the next step, the next loop will begin, as I talked about. So this process runs for as many epochs as you specify. The model learned the weights. So that's what happens in the background, as well as the intuition of why, what the network net input is doing, what the linear activation is or is not doing, what is the drawback of having the linear activation despite the simplicity of that, and then how is error related to cost, and why can we, how to understand gradient, why can we use gradient to improve the model to reduce the cost by using the gradient. It has something to do with the optimal weights. And after that, it's the mechanistic steps of calculating the update. All right. So that's the intuition of the process behind the Adeline. Just think about it. If I can explain this model using fairly intuitive language in 20 minutes, the model is good. And the model works, really. So the model not only works and not only makes sense in theory, the model can even make sense when you use language to describe it. Sometimes math and English doesn't go along, but if some math can be explained by English, that must be that the math is good. Does that make sense? Great. If you understand Adeline, you will have such a better time in learning neural network. because neural network, in terms of the mechanism or in terms of the black box, you know, if Adeline model is a black box, you're opening the black box, then the neural network is a black earth. So it adds that much of a complexity to the model. But if you take a closer look at the every step of the neural network, you can see a remarkable level of similarity between Adeline or logistic regression with the neural network. It's, you know, millions of black box add together, it becomes a black giant, which is the neural network. It's not much different, actually, if you understand how the inner workings. All right. Any questions? Any need to discuss? We can discuss. You know, we can spend 5 minutes. If there's still anything, one step that doesn't make sense to you.
Can you go over? Sorry. Can you go over the gradient again? What gradient is? Gradient.
Good. Yeah. Great. So here, let's use a simpler example to explain. Otherwise, we can't make a visualization. If we can't make a visualization, it's harder to explain. So assume that we only have one variable, that's one, and W1. We don't have anything else. It's a very simple data set. And it happens that, just so happens that the variable can be used to predict as long as you build the model well. We also have a bias, but the bias almost has nothing to do with optimal model. It's simply a adjustment of the location. So now we have one thing to optimize. We have the net input. You know, hopefully the one variable case, a simpler case, will make it easier to imagine what's happening here. It's simply, you know, multiplication plus the bias is the net input. This does nothing. Then we have an error. So suppose that we have take a perspective of one training example. We have a customer who did not churn. Let's see. We have a credit card customer who did not default. This is a good customer. The customer is paying the debt on time and have no late payment. So the Y label would be 0, no default, right? And you started with random weights, and it just so happens that the random weight multiplied by that variable, which can be income. Let's see. This person has good income, but you happen to draw a random weight which is negative, which is let's see, which is positive. Let's say it should be negative because income should lead to lower probability of default, right? So this weight should be, ideally it should be negative, but you happen to draw a positive weight, a small weight, which is positive. So multiplied by income, you get a very big. Income can be big. You get a very big net weight, net input. Then this phi, after activation, it's very big. It's very big. It could be 10. Let's see, but the true label is 0. So you have an error which is negative. This model clearly is not predicting well for this case. So the job is for gradient descent to do. Now we have a negative error for this case, for this customer who negative error, for this customer who didn't default. And with this error, you find yourself very high in the curve. When you calculate the cost, the contribution to cost of this particular case, this particular customer, for a weight that is, let's say, I said you happen to draw a positive weight, which is here. It's a positive weight. The ideal weight should be negative, should be to the left of the current weight. So with this weight and with this error, you find that the current cost function is here, up in the curve. The next job, think about your objective. Your objective is to reduce your current weight to go to another place, which is W1 prime. So you want to reduce the weight. By reducing the weight, you want to have a delta weight, which is negative. You want to apply a negative portion to the weight so that it can be reduced. That makes sense?
Mm-hmm.
Yeah? Okay, so your objective is to get this. Before you get this, you happen to see that here, if you calculate the gradient is greater than 1. I mean, not greater than 0, and it could be well over 1, but at least it's positive. So you see that your objective is to reduce the weight. Your gradient is larger than 0. In this case, you need to reverse the gradient, right? You need to reverse the gradient, and so delta weight is calculated by negative learning rate times the gradient. And now we only have one weight. So that's how gradient can be used to find or at least get closer to the optimal weight after calculating the gradient. So this connects the dots, but maybe you still have the question, why? Let's see, why gradient? Why not something else that's even negative? So you don't have to multiply or reverse the direction. The gradient makes sense with a little bit more explanation. Let's say we compare two random draws, version 1 and version 2. Because of their different location in the curve, in the cost curve, their gradient is different. Make sense?
Mm-hmm.
Gradient 1 and gradient 2. Okay, and you observe, and this is the sort of the ideal weight location, and this is the current weight about version 2, and this is the current weight version 1. Now, which gradient is bigger?
Second one.
Gradient bigger means slope is steeper.
Yep.
So that's version 1, actually.
Yeah, that's what I
Version 1, yeah. You probably meant to say the right one. Anyway, the version 1 slope is steeper. That means G1 is bigger. Slope is not as steep, so it's smaller gradient.
I guess.
And also, yeah, which weight needs to be adjusted more? That's also the version 1, right? So as you have greater gradient, it signifies that the weight needs to be adjusted to a greater extent. So gradient and the weight adjustment is somehow associated. You can use the gradient to do that. That's why.
Got it. Thank you.
Yeah. So that completes the loop, and the rest of it is more intuitive. Is that good, Ifras?
Yep. Thank you so much.
Perfect. Great. Anything else? Any other questions?
I have a question.
Yeah,
so
go ahead.
do we always start with some random weights? How do we generate those random weights?
Yes. Okay. An alternative to that. Let me talk about the alternative. The alternative is to use 0, right? Because you don't have. Because you don't have a good guess. So either you start from random or you start from all 0, right? Starting from all 0, let me see. Based on the literature, it does have some negative effects. It doesn't help in pushing the first optimization step. But the reason why it has something to do with the math. I'm not that familiar with the literature. I mean, in terms of why, I just know that in industry as well as in research, you would almost never start with zero, wait for all. If somebody, if some of you know better about this background, then feel free to chip in. How do we go about randomly generating? That's a good question. You don't want to generate something that is huge. That doesn't help. A huge weight, well, a weight of that size doesn't really happen in real life in data science projects, because remember, we have rescaled the x variables, right? So the x variable will have a scale of between 0 to 1. It's standardized, or it's min max normalized. With the normalized weight, with the normalized x variables, the weight does not have to be 500 for a model to, I don't think this ever happens in real life. But if that happens, that means the model is overfitting to the training data set. With rescale data set, the weight region is typically between -3 to +3 with a good model. The larger the weight, the more important the variable tend to be with rescaled x. So you don't need this big. How to go about that? We typically, in theory, we draw weight from a standard normal distribution with 0 mean and 1 standard deviation. In terms of implementation, you can take a look at the initialization step. Let's see, it should be here. So we create a random number generator by using the NumPy random package. And then we generate the random by drawing numbers of size n+1, which is the size of the vector for the weight. We draw the number from this is standard normal distribution with location as the mean, with the mean 0 and a standard deviation of 0.01. Sorry. So in order to get very small weights, we modify the distribution of the standard normal. We draw from a very small, very tiny normal distribution. This is -1. This is +1. It's very close to 0, so that you get very, very small weights. You can have something like that, so that the optimization can start somewhere, but it doesn't go too far off, and to avoid a very long learning process. If you have a weight that big, it can take a long time to converge to the right region. That makes sense?
Yeah, thank you.
Yeah. So with the initial draw, with that random state, the specific random state that you can replicate, you get weights like these, 0.0062, very close to 0, but it's not exactly 0. This is not exactly 0. You can't get exactly 0, but it's very close to 0, maybe 1 to the e -6 or 7, so that the digits cannot be shown. So that's why. Any other questions? So we did. Yeah.
Can you explain this eta a bit? Why we have to have
the
it
eta?
low eta? Yeah.
Yeah. Okay. So two parts of the question. Let me see. I really don't want to say things that you already understand that waste our time. So, do you understand the reason we need this, regardless of how large or small it is?
Yeah.
Why do we need an eta? You don't have to explain. I mean, simply say yes or no. You know or you don't know.
I'm not sure if I know.
Okay, so let me say that. Now, the purpose of eta is really, it's an empirical step. So it relates to the empirical training of the particular data set to the particular the problem, the prediction problem. There isn't really an optimal ADA. You just have to find a value that's in the right range. And the range doesn't have to be very tight and small. Sometimes with large variation, you still, in the end, what you care is that you have a good enough model, right? Even if you have to train for 1 more minute, it doesn't matter. With a worse pick of the learning rate, your training time could be increased by 5%, but that's fine, right? So, so with small variations, ADA is fine. The model will be fine. But why do we need ADA? The reason why do we need ADA is because, look at this. Weight update really ties to how the model is improved. Delta weight directly affects how fast the model is improved, right? In comparison to the weight. So if delta weight is far off to the actual weight, it could make the model worse, or it could learn very slowly, right? But the calculation of the delta weight is simply delta weight is simply a function of the gradient. But who knows what gradient will be? Gradient could be huge, or gradient could be small. You don't know. And during the training process, gradient changes. So this is sort of like a scaling factor. That's the only reason it's there. With the scaling factor, you can adjust how fast or slow the learning goes, and that's all. By choosing a small learning rate with Adeline model, because of the linear activation, you can really speed things up. If you don't put this in, for an Adeline model, for the very simple data set that I use in the demonstration, this could train for maybe 1,000 times. You're still not seeing a good enough model with small enough, the model can explode and you never see the best model ever. With the scaling factor chosen to be small enough that's in the appropriate region, in 10 epochs, you already see a better model. So that's the only difference.
Okay, got it.
Yeah. Anything else? Can we declare victory? Yeah. So no questions means understood. I mean, you don't, it doesn't mean that you can perfectly remember everything. It doesn't, you don't have to. But at the intuition level, you can tell yourself, now I know what it's doing. Now I'm getting it. That's it. That's good enough. With more repetition, with more exercises, with more implementations, you pick up additional things. You'll be better able to connect the technical with the intuition. By the end of the course, I'm sure you'll give a version of the Adeline model explanation that's probably better than me. I have no doubt about it, because you want to learn it, right? You want to learn it, and you want to improve your understanding, and you want to be able to explain it to other people. So you have better motivation. I'm sure you will do better than me. So we can move on to logistic regression. And you can see that it's so, it will be so peaceful, the process. There won't be too much of a struggle, because you already understand the Adeline model. So logistic regression, we did that last time. That's mostly for the Adeline model. All right, recall this is Adeline, because you see a linear activation, right? That's a sign, that's a signal. This is very much consistent with the graph I shown earlier in the previous slide. With the 2 layers, this is only 2 layers, and these weights are these weights belong to the output layer, the output unit, but it's marked on the line to show that the line is weighted, right? And each of the element of the weight vector correspond to each of the input space, the feature space. So with the linear combination, you get a net input. With activated value, you are able to calculate the error and feedback, perform the optimization process, update the weight, and go on. So that's what it does. But logistic regression, why logistic regression? Precisely because of this guy. You know, it's not good enough. It produces error that's huge, and it requires a very small learning rate. And sometimes you just after trying a few things, you try ADA is 0.01, thinking that's good enough. After training a few times, you want to kill yourself because it's still nowhere close to that. So that's why I said, you know, with Adeline, when you try different things for ADA, you want to change that by a factor of 10. So, you know, if that fails, if you think that's still too large, divide by 10, 0.01, and try that. If that doesn't work, divide it by 10, and eventually you'll get there faster. That's how, you know, that's the nature of the impact of the learning rate in Adeline model. We want to replace that with something that will squeeze the value so that the error space is not so big. For extreme values, we don't really care what the actual we don't really want to retain the extremity of those net input, and we want to get rid of those extremity in doing the activation, because the extremity doesn't help really. You know, extremity is caused by only one reason. If the data is scaled, that's because the weight is huge, right? Because, you know, extreme input is only because one of two things: extreme input or extreme weights. If the input are rescaled, you don't have extreme input. Then the only reason the net input is extreme is because the weights are extreme. We don't like extreme weights. So we want to get rid of those. We want to, you know, help the model learn smaller weights. So that's one thing. And another drawback, or maybe you can't really blame the Adeline, is that with this we cannot really have a realistic estimate of the probability of, let's say, default. You know, so that's probably why machine learning models weren't used that much in business, because that's not helpful. It's purely used in computation. With business, they wanted to explain things well. With linear activation, the activated value lies in the real number space. It could be very small. I mean, it could be negative extreme or positive infinity, and this doesn't help explain, you know, how likely the customer is going to default or not. Business folk can't use them. But with logistic regression, you can do that because of the Sigmoid function. I'll talk about a little bit. It's quite intuitive. You probably already understand these. I don't have to talk too much. Time check. Okay, great. The reason why logistic regression is called logistic regression is because there's a logit function component in the model. So previously, with the Adeline model, you take these out, observe this part. What is this? This is the net input, right? This is a weighted sum of the signals. That's a Z. Without the logit, you have the Adeline. With the logit, it becomes logistic regression. That's the essential difference. And why logistic regression is popular it's not only because it's a improved version of the single neural model, it is also very popular in statistics fields. Because why? Because if you take the probability of, let's say, credit card customer default, and the probability is, on average, is 20% or 15%. If you take that probability, you divide that with the rest of the probability, which is a no default probability, and take a log, it becomes a concept which is called log odds, which is, sort of a way to measure your winning odds. In casino, in gambling, it's a fairly common clause. You can say that this racing horse, horse race, this horse has winning odds of this much, 55-1 or something like that. In lottery, also, you have a winning odds. This is that concept. This, the difference between the chance that you will win or it will win versus the chance that it will lose, right? If the log odds is 0, that means the chances are equal, split, 50-50 split. You have 50% chance win, and 1 minus 50 is 50% loss. The division is 1, log of 1 is 0. So 0 is a line to draw between something that is more likely to win from something that's more likely to lose. So that works well for business, but also it works well for statistics. If you have a P and you calculate the log of the odds, it can directly, you can hook up with the real line space net input, because this function can take any number, right? Log function, if to refresh your minds, log function is like that. This is 1, right? As long as what's inside the parenthesis is larger than 0, the function is valid, and the log function can take the entire real line space, right? So essentially, it's somewhat like y, in regression. In a regression model, y is the dependent variable. It potentially can take any number. You equate that to the, this form, which is very familiar, which should be very familiar in terms of linear regression. You can estimate the x's. Now, with the change, with the use of the Logistic function, you somehow transform a probability, which is between 0 and 1, to a real line space, which is between negative and positive infinity. You can equate that and estimate the regression model as is. So that's why it's beautiful. It's not only useful in machine learning, it's also popular in stats. And then with stats, you can have economics, education, and many other policy making can use that empirical method to analyze the problem. So that's why logistic regression is so popular. But before I know about machine learning, I didn't know it. Logistic regression probably has longer history in machine learning than economics. That's kind of ironic. So far, so good. Great. Now, how does the Sigmoid function come into play? So the motivation to find the sigmoid activation function is because of the linear activation function. With linear, you can't really limit the error space. It can go, the prediction can go really large, but the true label of y is only 0 and 1. So ideally, you do not want the activated value to exceed or go into these, these region. You want the activate value to only remain in this region so that error is all defined and sort of, or constrained. You don't want them to be, and also you don't want to leave too much extremity from the net input, C, and go into the gradient descent, because that will make the gradient too big. So because of two reasons, it just happens that there's a function sigmoid which does exactly that, but with a sort of a funny line, with an S line, quite smooth. This function will turn the real space value, C, into a value which is definitely between 0 and 1. So, and because of the feature of this function, it catch up, and logistic regression is small. But observe the behavior of this function for any value of the Z net input that's greater than 4 or smaller than -4. The value is almost going to be close to 0 or 0. It's never going to be exactly 1 or 0, but it's, to say the least, it's an extreme. It represents the extreme end of the activated value. So that's all we care. If the net input is greater than 4, we don't really care how much larger is there. We just know that with this, the prediction is very much likely to be the positive, the churn, in terms of churn and no churn, not churn, default behavior of customers. The predicted value, which is the activated value, is very much likely to be default without too much doubt, So it doesn't really matter how close it is to 1. It's going to be 1. Prediction is 1. So this function smoothes out the extreme values and helps with the learning, right? But observe the portion between -1 maybe, -1 to +1. What does it look like? It's like a straight line. This is what linear activation exactly is doing. This part between -1 and +1, it's like linear activation. So that's another beauty of Sigmoid function. It not only get rid of those extreme values, but it preserves the upside of the linear activation, because it's simple to derive. When you calculate and when you implement the gradient descent, this part is easier. And for the learning process, it also helps the model learn, as well as far as the net input is in this region, which is a well-behaved region for the net input. So for these multiple reasons, Sigmoid function is latched onto, and logistic regression is implemented. And when you look at the overview of the process, the only change you can notice is the sigmoid activation, without anything else being changed. Of course, this will impact the output, but as far as the learning goes, the only thing that changed is this. So question, where is the conditional probability attained? Probability is a quantity to estimate the likelihood of something happening, right? Probability is between 0 and 1. One benefit of logistic regression, or the sigmoid activation function, is that the activated value is right between 0 and 1. So you can, and the larger the value, the more likely we are going to predict the case to be a default case. The smaller or closer to 0 the value is, the less likely we're going to predict default, or the more likely we're going to predict no default. So the activated value is somehow very intuitive to understand, and it's consistent with the notion of probability. Although in the real number sense, for the model doesn't know that this is like probability. The model simply squeezes the values between 0 and 1. The model doesn't matter. The model doesn't care. But for us to be able to interpret what this activation function is doing, it's very much like a probability estimation. So that's why it just so happens that we directly use the activated value to sort of to imitate the probability of something happening. So tying that back to the model, which step is the conditional probability obtained? It should be right after the activation. So try to find where the activation is, and the result right after that and before the next step, the result is the conditional probability of the logistic regression model. Yeah, you're able to find that? It should be here as indicated by this notation, right? Right after Sigmoid activation, you have an activated value for every case in the training set. If the model is trained well, that quantity, that activated value, you can use that value to represent the estimated likelihood or probability of the customer defaulting the account. Time check. So I should be spending 40 minutes. Anyway, any questions here? So if the model is only different by the activation function, then the implementation should be quite similar, right? The steps, the overall structure is the same. You have forward prop and backward prop. So the only difference would be the forward prop. Is that right? Let's check that. So that's the thinking process. Only difference is the activation function. So when you train the model, the implementation steps should only be different in terms of the activation step. Now let's use the example demo. Before we take a look at the implementation codes, here I like to talk a little bit more about data pre-processing, as well as train test split that we talked about last time. And after train test split, always use hypothesis testing to evaluate the split. And I think this concept is well received because almost all of your homework in these two questions are good. So I don't have to talk too much. Performing train test split in homework 1, the last two questions, I asked you to split the train test by using the original data set. So with that, you will split that data set into a train and a test. With that, you perhaps need to separate the input and the target data using the train and the validate, the train and test set. So you need to do 2 split afterwards. But you can reverse the order, and some of you have already done that. So you can first separate X and Y, and with X and Y data set, you can do the split. Also in one step, you will get 4 data sets, X train, X test, and Y train, Y test. So that eliminates one more step. After doing the split, you should evaluate the structural similarity by using hypothesis testing. Usually, you know, if the target variable is binary or at least a categorical variable, you should always check proportion of Y labels in the train and test set to make sure. If X variable, if there are too many X variables to check, then you can either use a for loop or to do a systematic check and only look at the proportion of significant results, right? By default, you would assume that the results would all be not significant, which means p-value should be greater than 0.01 for all the tests, and that will sort of provide you evidence of a healthy split. But even if you see a couple of significant test results, as long as they don't take a substantial portion of the data set or the number of variables, and as long as the Y data is splitted healthy, you should have not a big problem in terms of using the test set. Quickly showing the code. This is the Adeline, and now begins the logistic regression with the data set, the same data set. With that data set, first take care of the age. I calculate age by using the year of birth, and then create the X and Y. So this time I create X and Y first, and many of you have already done that. So I just mentioned that. Create the X and Y, make sure you get rid of the ID as well as the target variable from X, and Y is a simple column. And you provide the X and Y both together to the training test split. It will split, it will spit back 4 data sets. It will split each set in the order of training test first and finish one set before going to the other set. That's why you have 2 X's and 2 Y's. The first X is the train, the second X is the test. With that, check the proportion of label 1 in the target variable. You know, p-value is very large, well above 0.5. The test failed to reject the null, so that means a healthy split. I skipped the X because I know that all the X are good, but you know, if you're diligent enough, you should check. But I like to talk about the transformation pipeline, not pipeline, column transformer. So far with pre-processing, if you already know this, I talk about this in the advanced programming course toward the end of the semester of last semester. If you already know this, you can skip this part. So column transformer makes it easy to, it does not only make it easy to pre-process the training set. The real benefit here is to, because now we have the train and test, the real benefit is to use whatever is that you have built up for pre-processing the train set to apply to the test set and do it in one step. That's a real benefit, that you don't have to do the same repeated steps for the training set to repeat it on the test set. And with the difference of the train and test set, you can't really do that. The process will become very cumbersome. With transformation with column transformer, it's much easier. Remember that so far for the homework, we did mostly two conversions, sort of. One is categorical variable. You basically use create the flag variables and use the k-1 rule, discard one of the label. Every categorical will be converted to a bunch of flag variables. So that's one type of pre-processing. For interval variable or numeric, but sometimes numeric variable can be categorical. So interval variables are those that have continuous values. We would need to use for, let's say for Adeline and logistic regression, we use min max normalization. For regression, we can use the standard scalar, the z-score. But anyway, it's just a difference of the scalar. For interval variables, we use such a scalar, right? So categorical variable will produce a data frame that has flags, and somehow you need to merge that with the main data set, right? That's part of the homework. You need to merge the data set. You need to copy the ID, and then use the ID to do an effective merge. Otherwise, the rows may be mixed up, then the merge will mess up with the data set. That's not good. The process is cumbersome. Imagine doing that for the train, and then you have to do that for the test set. It's kind of a lot of codes, and you can easily make a mistake. Interval variable is easier. After using the scalar to rescale the variable, you still get a data frame of the same dimension. So that's easier. But then you would still have to merge these two. You have the flag variable and you have the data frame for the rescaled interval variables. You need to merge them. So the whole process is not good. Transformer, column transformer, eliminate this process, you know, as long as you follow the syntax. So what it does is it does those steps in the back for you. As long as you create the thing correctly, you need two scalars or encoder. We will use different terms to refer to the same thing. One Hat encoder is an encoder to encode the categorical variable. Range normalizer or a scalar is a scalar, which can also be understood as an encoder. You know, it rescales the values. You define these two, put them into the same transformer, and define the labels correctly. What are the labels to apply the one Hat encoding? This is one Hat. What are the variables to apply range standardization? The transformer will then identify those different columns for the appropriate transformation, and after transforming the values, it will glue the columns all together and spits back to you one data frame. So it does the merge for you automatically. You don't have to do that, and the function is robust. So, you know, it's just so easier after that. But that's not only that's not the only benefit. The really good benefit is to streamline the test set, and this is critical. Without transformer, you probably do this. Let's say for rescale, you need two statistic. You need the mean and you need the standard deviation of the variable, right? So for train data, so this is train. For train data, to rescale the variable, you need to do this. To standardize the value of the train data, and this is also train TR. The mean and TR, the mean and standard deviation of the train set. To standardize the test set, same formula, but what mean should you use? Do you use test? No. So this is the real trick here. to rescale the test set, you should not use the statistics of the test set. Doing this is like committing a crime in data science. And why? Because you are not supposed to know, and the model is not supposed to know the real statistics of the test set. It should be hidden. It should be really hidden. It should be locked up. But you still need to do the transformation because the model has to conform to the format and the rough region of the training set to use the same model. So you still need to rescale the test set, but you use the train statistic always. But you might say the train set average may not be exactly the same as a test set average. Yes, that's absolutely right. But still you use the train set statistic because you have no knowledge about the test set. You hope that the test set is close enough to the train set, but things happen. With random variation, you could get, randomly deviating points. And the purpose of using the test set is really to test your model with the condition that there might be deviations, right? So you have to accept that reality. So no, never use the test set statistic here. So that's one caveat. When you have to manually do those steps without using the transformer, you have to always use the train set statistic. So that's what the fit is doing in using the transformer. Now, scalar is a transformer. Encoder is also a transformer, but they are not column transformer. Column transformer combine multiple transformers together. When you use the fit, it is calculating the statistic of the data set. So you only apply fit transform to the train set so that it gets the statistic from the train set. When you do the pre-processing for the test set using the column transformer, you only apply the transform. So it uses the train set statistic to transform the test set. If you somehow use fit transform on the test set, what it does is you will notice that your test set performance tend to not always, but tend to also be good, to be good and close to the train set. But that is not really a robust testing mechanism. So what it does is, if you do this by mistake, use the fit transform to pre-process the test set, what it does is it will give you an illusion that your model is doing good enough on the test set, but when you apply the model to the real data, to the not real data, but in real operation, you'll get surprises. The model will not perform as well because the model is somehow, this is kind of a cheating process. In testing your model, you're cheating yourself, or you're giving yourself an illusion in terms of evaluating the test set performance. So that's why I have made this point clear in the demo as well as in the homework. So be careful. These two have different results. Any questions? We're close to Sigmoid. I think I don't have to talk too much about this. This is the way it's implemented. With the Adeline, you simply multiply by 1.0. You can even skip this point. But the reason I did this for Adeline is to just create a placeholder so that when you calculate the logistic regression, you can copy the entire code, but only replace this line, right? In Python, to implement E, we use numpy.exp, with the natural number exponential. Don't forget the negative sign here, and Z is Z. But also for Z, because this is an exponential. If z is huge, if z is 1,000,000, e to the power of minus z is going to be, or maybe, if z is 1,000,000, this probably isn't a problem. Minus z is minus 1,000,000. E to the power minus 1,000,000 is close to 0. It's a long decimal, but it's close to 0. Maybe not a problem. But if z is minus 1,000,000, this e to the power of double minus is positive. E to the power of 1,000,000 creates a huge number for the computer to handle. Slows down the computation. It's not necessary. So we use a NumPy clip function to really get rid of those extreme values, because we don't care about those extreme values. But in the code, it's clear. You can take a look. So, and that's it. We can we can look at the for loop process to see what is different. Not this one. Okay, so these codes are for pre-processing. The test for the test set, always use a transform, not the fit transform. And initialization is mostly the same, with the difference only being the eta. Eta is not so small anymore. It used to be 4 decimals, and now it's only 2 decimals. And with this eta, it's adequate. It doesn't have to be too small. The weight, initial weight is the same because the same random state. Now the for loop, put the for loop together. The only difference, besides the cost, the only difference is the activation part. The other parts are exactly the same, exactly the same. You know, here it's a 2-step process for activation. Besides the Sigmoid activation, which is this line, you also have a clip to get rid of the extreme values, right? And then the rest of the forward and backward prop are the same. And the only other difference, which is minor actually, is the cost function calculation. This doesn't mean that the cost is fundamentally changed. It simply use an alternative formula of thinking about the penalty. You can think of a penalty as the sum of squared error, which is, you know, the one that we use in the Adeline. But for logistic regression, because it's so popular in the economics and other disciplines, people like to associate probability with the cost function. So here, you know, by convention, we also use the probability. So this cost formula incorporates the what's called the cross entropy, binary cross entropy estimate to calculate how much variation and how much, you know, distances is there between the log likelihood of the data set and the sort of the optimal model, where the optimal model is. So it's calculating how much room is there for the log likelihood of the data set to be improved. That's all about that. You know, you simply need to know how to implement that. For the literature in the background, I don't think that's critical. So with this implementation, the only necessary change is the activation function. We train a model with the eta, it's adequate. The cost reduced from 400 to 100 something. You can see the curve. Initially, the model became worse because of, I guess, random draw of the parameter. And somehow it has to do with eta, maybe. Eta is too large. Initially, it caused the model to be worse, but with one more training, it gets back on track. You can, based on the curve, 10 epochs is clearly not enough. You can see the curve, you can see the trend of the curve, it will go on. Probably needs a few more training. But with only 10 epochs, let's look at the result. The train set accuracy is 87.7. The truth is that a well-trained model for this data set can achieve an accuracy of 93%. So this model is getting there. With a random model, accuracy might be 78%. So the model improved from 78% to 87% for the train set. It has room to improve, but with only 10 epochs, that's how the model is performing. With the test set, let's look at the test set. So the test set is really the other sample set. If the model is overfitted, test set performance will be worse. Train set and test set performance is close enough. This data set, ideally, a model can perform at a 92% level, accuracy level. Model is only trained for 10 epochs, it achieve 87%. For the test set, it's a real out of sample test set. So it's a fair testing. And with that, test set performance is slightly lower, but not too much. So here is the thing I want to discuss. All right, I like to talk about the learning process. So here is what I would like to talk about. With the implementation I demonstrated, we are not able to draw lines such as these. These will require train and test set to be evaluated at every step of the epoch. We can't do that, but we can kind of, plot these 2 points in the plot and think about what scenario is our model right now. So a model can have multiple issues. One is a high bias issue. What does that mean? Bias means error. High bias means the model suffers from a higher error than expected. If we, if you're familiar with the problem, and let's say, and you know that a benchmark performance is somewhere in terms of accuracy, but your model is performing much lower than that. Let's say an ideal level of performance may be 90% accuracy, but your model is only standing at 80%, even after you train for a long time. And doesn't, with longer training, it could overfit. So with appropriate amount of training, your model is still at 80%, is 10% lower than the optimal. That means the model is has a high bias problem. The model may have room to improve up to 90%, but you have to find the way to do that. So that's one scenario. You also have a high variance problem. What does that mean? That means your training set performance is very good. If you expect the model to perform 90% accurate, your training set is 90% or even higher. It could be 95%. It's possible with overfitting. With overfitting, you can get 100%. But when you look at the test set performance, it's much worse than the train set. It's even worse than the ideal level. So when you compare the two have a large difference. That's what it means by variance. When you average the result, you get the ideal level. So the bias is small, the error is small, but in that case, you can't really trust your model to perform well in new data, right? Because test set is like a new data. If you apply the model to the new data, you expect the performance to be much worse than the training set. That's what it means by variance. The variance of the model performance is large enough to create risk, and you can't accept that risk. You can't accept the model doing poorly on new data, especially when you have evidence to say that. So that's when the model is suffering from high variance. Could you have something like that? Train and tests are both below the ideal level, and train and tests are also have high variance. So high bias and high variance, that's rare, although it could happen. That's rare. So that's why we don't have that fourth scenario. So the third scenario is really you have low bias and low variance, and the two have a good balance with each other when you have enough data sets. This is the size of the data set. When you have large enough data set to support the training of the model, the performance of the model on the training and test set converge, and they converge at an ideal level of the accuracy. So let's look at our model. We have the train and test set. We only have a snapshot. We don't have a curve. But imagine it's somewhere, the data set is not too small, so it can't be at the left side. You can imagine that it's somewhere in the middle range of the data set size. So the size of the data set is adequate. If the model is good enough, it should be close to the optimal accuracy level. Currently, train and test set has performance of 87 and 85% accuracy. I tell you the true, this is rare, you don't really know this in real life, but for this data set, I know the truth. The truth is the model could achieve 93% accuracy. So which scenario are we? Is there high bias, or is there high variance, or is there none of these?
I think it's high bias.
High, again?
High bias.
High bias?
Yeah.
High error, right?
Yeah.
There is a distance between the optimal, the ideal level accuracy and the current accuracy level, but the train and test performance is not so far off. They're pretty similar, right?
Yep.
So that's right. So the problem is high bias, and it's somewhere here, right? No, we're here, and you see that let's see, for the training set, we do observe the cost curve, which is, it goes worse at first, but it then becomes better. It's here, and the this line may not be so close to the axis, and if you keep training the model, it can go better. So the cost can be lowered, further lowered. The model has only being trained by 10 epochs, and typically 10 epochs are not really enough. So to solve this problem, we're going to train for longer times. So that's what we're going to do. So we're going to train for 10,000 epochs. That's a long time. That's a large number. We only trained 10, but now we're going to train 10,000. Let's see what happens. And to do that, we will need to reinitialize the initial values. The only change is the epochs. We change that to 10,000. Everything else remains the same. I combine the two cells, the initialization and the implementation together. And this probably ran for 15, 20 seconds, maybe, if I remember correctly, because the data set is not complex. With that, this is the cost curve you observe. With 10,000 epochs, the cost curve almost flattened. With about 1,500 epochs, the cost curve is not really moving downward. So, in a way, the model has learned everything that it can be learned by this model at this complexity. So, can you imagine what will happen with this model after training 10,000 epochs? Let's look at the training set accuracy. It's 100%. What does that mean? It correctly classifies
Overfitting?
every point. You may think so, and it's a very good point. Let's see. I will discuss that. Right? So you see, at least you see the improvement, right? At least you see the improvement from 85%, 87% to on a training set. It improved from 87 to, way over the target, 93%. Hold on. I think I might have made a mistake. I think the truth is 99%. In this data set, I think I made a, I was confused with another data set. But for this data set, it can potentially, the true labels are 99% separate. The cases are 99% separable by ground truth for a fair model. So, but for the training set, it goes to 100%. It goes to the top. With longer training, at least you improve the model dramatically, right? Is there overfitting? So, by the way, the answer to this question is, it's high bias, and how will you improve it? To train longer in this case. So then the question is 100%, is it realistic? Every time you see 100%, it's not entirely realistic. There's something going on there. So one question you have is, one obvious question is, do we have overfitting? What will you observe if we have overfitting? Overfitting has a problem exactly because it produced a model that has high variance. Overfitting leads to a model that performs super well on the training set, but it performs poorly on the test set. That's when the high variance problem occurred. So if we had overfitting in this model, we would observe training set performance to be very good, and that's the case now, 100%. But we would expect the test set performance to be at least lower than 92 or something, has a large margin. But you take a look at the training set, test set performance, it's also very good. It's 98.8%. So in a way, get rid of this line. The real line should be here. Training set is slightly above that, 100 versus 99%. And the test set is probably here. So it's like this case. You have good bias and good variance balance in this case. But, it's still puzzling. Why 100%? One reason is that this data set is easy to separate. The ground truth is easy to get for an adequate model, and logistic regression is an adequate model. So it can get at least as good as 99% with enough training. With more training, you cross the line. You tend to remember the data set. It is overfitted a little bit to the data set to the point that it doesn't even make a few mistakes. But those parts of overfitting only carries the model so far to the point that it makes slightly a little bit more mistakes in the test set. It doesn't create too much of a trouble in this case. Does it happen always? Definitely not. With overfitting, the test set performance can be really bad when you have a high variance problem. Here, even with slight overfitting, why do you have good test set performance? Just because the problem is easy to solve. That's it. So even if you have overtrained the model doesn't go too far off. You know, with a better model, you could have. That's why we use regularization. With a better model, you could have train. I can't write here. With the train accuracy maybe 99.5%, and the test set performance maybe 99.2%. So slightly worse train set accuracy, but slightly better test set performance. That's the reason we use regularization, is to reduce the chance of overfitting. Make sense? Great. I think regularization is the only thing left for me to say. So I'll just quickly talk about these because you'll do the homework this weekend, and this part is recorded. What does regularization does? It modifies the cost function. I think I talked about it earlier, the first week or second week, but here now you know what the cost function is, right? If I flip to the logistic regression, so this is logistic regression implementation, and cost function is calculated at the end of each epoch. The cost function here is cross entropy, binary cross entropy. So that's the cost. Without regularization, this is the cost that you would calculate. And that's, this is the function that produced the line, the curve in the plot. Now with regularization, it adds something to this, cost function. So it increases the cost a little bit, but it's not as simple as that. When you add another portion, and that portion also has something to do with the weight, then in the optimization process, the model will somehow distribute the optimization differently to different parts of the penalty, the cost function, so that it will balance out the entire cost, right? The objective is to reduce the cost, but instead of reducing this part, you can also reduce that part. If reducing one part leads to increasing the other part, the model will not do that. The model will try to minimize everything together in a balance. So that's a mechanism that regularization is able to control the learning process. And again, I think I asked the question, for the regularization to be minimized, what is the scenario? That's when all the W is 0. This is the part that's added to the cost function, and the model will try to minimize this part as well as the original cost function. The model will balance which part to lower to achieve the best possible result. But for this part, in order to reduce this part of the cost function, the model simply has to, adopt the weights that are all 0. And clearly, this would not be a satisfying model. With all the weights being 0, the model is not doing anything. It's an average, using the average of the sample to predict. That's rarely going to be a good model. So the model eventually will settle between 0 and the version of the weight that is learned without regularization, right? So without regularization, the model somehow learned this part. But when you add in the regularization, it will, let me see if I can do this. Very good. Precision, you know, I can just raise out those cross line. The model, regularization pushed the model to reduce W in the direction of 0. And what it does really for the model is it avoids a case where the model learned a W, which is very large, like, 100. With overfitting, you could have a weight that's learned by the model as large as 100 because this works. The model finds that increasing this weight works. It increases the accuracy. Why not? So the model will try to overfit to the data by learning excessively large weight. But with regularization, you will prevent the model from learning this because as soon as the model does this, this part will explode because you take a square. If this part explodes, model will not do that. So that's the intuition behind regularization. The effect of that, you can see that very clearly in the model training. So let's see, with here, it's the training after training 10,000 epochs. Let's see if there's overfitting. There is, but not too much. But what's a sign of overfitting? Even if you don't have high variance, you have low variance and low bias. Where is the overfitting? When you print out the weights coefficient, you observe something like these. The weight space is, the weight vector has 17 variables, 16 or 7, or maybe 20, something like that. One of them is bias, it doesn't count. But you rank them in terms of absolute values. The largest absolute value is close to 50. For a model to learn a weight which is as large as 50, you can be damn sure that the model is there's something going on for the model. The model has somehow learned a trick to increase this weight to get the accuracy higher. This variable turns out to be the most important variable in the data to be used to predict the label. And by design, this is the case. But the model goes too far. The model is, the model kind of, played this trick by increasing this weight so much so that it tries to get perfect classification. But doing this will risk the test set performance. Yeah. So now we use regularization. The changes are illustrated in the cheat sheets. There's only one, or I'll talk about that already. The only change is the activation. So with this, I reduced the training to 200. I didn't go as far as 10,000 because doing that is going to achieve the same thing. With regularization, it will prevent the model to be even better. So at some point, the model will remain stable. As you can see here, the line doesn't, even if you zoom in, the model will stabilize over there. And if you compare the curve of this version with regularization with the version above, you see the line is still improving somehow, even after 10,000. And the model flattened after almost 2,000 epochs. From here, it's quite flat, even though it's increasing slightly. That's 2,000. But with regularization, the model stabilized at 200. So the model, almost never changes after that point because the added regularization did have an effect. It prevents the model from itching further to increase the weight in order to get the reward, right? And then with regularization, you compare the performance. The train set performance is reduced from 100% to 97. And that's already quite good. And when you calculate test set, it's closer to the train set than the previous version of training. So now you have at least the model doesn't get perfect. This is purely because of the regularization. But in this data set, in this case, either version of the model does a good job in terms of the test set performance. So there's not too much to compare other than knowing the effect of regularization on the train set performance. On a real life data set, on a less perfect data set, you can see more of a bigger difference between a model that has regularization and that the other model that doesn't have that. And after regularization, when you take a look at the coefficient, the biggest is only 7. So that's a dramatic difference between dramatic difference in terms of the size of the coefficient. The size of the coefficient can somehow tell you if the model is overfitted or not. So that's where you look. And that's it. 2 hours. Good. Now, since homework is due by the weekend, we can use this time for troubleshoot or any questions. It will be perfect if there's no question, but I don't believe that. But if you don't have question, you know, that's great. Make sure you submit your homework by deadline, or let me know if you have a question later. So we can call it a day and enjoy the storm. Storm is almost over, I think, right? All right, let's open this up. I'll stop share, but oh, yeah, why don't I, because I can't recognize some of you, but I think for everybody here, I can recognize. Abhinaya, can you turn on your camera? I'm trying to recognize faces. Yeah. Hey, Milan. Okay. Abhinaya, if you hear me, can you turn on your camera? 1, 2, 3, 4, 5. Okay. Right. Hello there. I'll try to recognize Sahitya and Abhinaya. I'll try to tell you apart. I'm not saying you're look-alike. I'm just bad at. I think I need some help from machine learning models too. You know, vision, image recognition. I need some help from machines. But thank you. Any questions?
I have a question.
Yeah, go ahead.
So for the desired accuracy, how do we define our desired accuracy? Is it the same for all the logistic regression model?
The answer is no, definitely. And the desirable performance is not so much dependent on what model you use. As long as you use an adequate model. Logistic regression is an adequate model for classification problems. And here's why. These models, you know, as long as the underlying pattern can be linearly detected, these models will be able to pick those up. For simpler problems, you will notice little difference between logistic regression and neural network. For complex problem or for super large data set, if the data is gigabits, logistic regression will suffer because of the optimization process. It will take longer to converge and it could break. neural networks is better in handling those. But as long as the model is adequate for the problem and for the data set, the ideal performance level is independent of the model that you use. The ideal level of accuracy is dependent on the nature of the problem, the quality of the data set in terms of if the cases are separable, mostly linearly by using multiple variables. Can you does the data really support such a model to do well? And the third thing is in real life, it relies on your, or domain knowledge can be helpful. So what it means is assuming that humans can perform the same problem, although with more labor, with more effort, humans can be able to do the job well. Let's say, in image recognition, humans can differentiate a cat from dog, can differentiate 1,000 different animals, or even small differences in species of the animals. If humans can do well, computers are expected to do well, given good training data and given good algorithm and enough time training. So, right, if humans make 1% error in classifying the objects in the picture, machines are expected to do as well as humans, so that 99% accuracy. That's the expectation. However, for a lot of business problems, as well as medical and healthcare problems, you can't expect human to do well even. For doctors to diagnose cancer, cancer tumor, based on images, doctors' best performance may be 90%. Doctors may miss a cancer tumor. Doctors may have false positive case, right? Mistake something as cancer tumor, but really it's not. So doctors can make these errors as well. So in that case, you would not initially, at least at the beginning, you will not expect machines to do better than doctors. You can expect machines to do as well as doctors, and that's good enough. So that's how you establish a desirable accuracy level. And that comes down to domain knowledge, right? If you understand, if you try to solve this problem in medical area and you understand how the problem is diagnosed clinically by doctors, you have a better sense of the expectation for the models. Any other questions?
Actually, I have another one.
Go ahead.
So, how do we know when should we use logistic regression model, or when should we use the Adeline model? Is the logistic regression model better for classification problem?
You know already. So I probably haven't said it open loud. As for Adeline model, it's really a learning opportunity. Once you learn logistic regression, once you know how to use logistic regression, you would almost always use logistic regression over Adeline. So Adeline is more of a learning opportunity. But if I modify the question to compare logistic with neural network, that becomes a real question. How do you decide when to use neural network versus logistic regression? I think a lot of times because the model doesn't do well enough, you try both. So that's a real motivation behind choosing them. It's not like, one model is destined or kind of, is perfectly matched with one kind of problem. So you use that model only for that problem. That's rarely the case. Machine learning in empirical, in applying machine learning methods, you typically apply a range of models as long as the model is suitable. A neural network can solve classification problems as well as prediction problem when the target variable is interval. Logistic regression can only be used to solve classification problems. So for prediction problems, when the target variable is continuous, you cannot really use logistic regression, but you have to use something else.
Okay, thank you.
Yeah. All right, any other questions?
Yeah, I have a question, Professor.
Go ahead.
Why are we clipping the values? Because we're already regularizing the numerical variables, and our weights are also not so high. And in that case, why are we clipping the values? What is the use?
Oh, why do we clip the value?
Yeah.
Take this example. If the z is negative 1,000,000, then the Sigmoid function will try to calculate e to the power of positive 1,000,000, right?
Right.
And that value is going to be huge, right?
Yeah.
And it will take at least a longer CPU time to calculate. But having that large of a value for the input really doesn't help. It doesn't help, on the margin. So numerically, it would be almost equivalent if z is 250 or 300, something like that. E to the power of 200 or 300 in terms of the activated value after Sigmoid activation is almost equivalent to e to the power of 1,000,000. Because of the equivalent result, we clip that just to save some CPU time. That's it. Yeah, makes sense?
Yeah, I was just having the doubt because we're already regularizing the numerical variables, and we're making sure the weights are also not so high. So I don't see the scenario where it would go to that extent.
Probably in real implementation, you would rarely have. I mean, you almost never have a z of that large. But I guess for beginners, the coding might have some problem. The initial, I mean, the variables may not be standardized properly, right? That could happen, right?
Yeah, right,
So,
correct.
I mean, not every student is as a good student as you guys are. So they may not be properly trained and they're messing things around. Their data may not be properly scaled. They have an income variable, which is 2 million. That will jack up the Z, right? So then computer may crash. So that's one scenario, I guess. But in the real impact, probably little. Yeah.
I have another question.
Yeah.
So the doubt is gradient descent the only optimization algorithm we use or we have? I believe there might be other algorithms as well.
I think there are different variations of gradient descent, but all of them have the same commonality in terms of gradient descent. There are stochastic gradient descent, mini-batch gradient descent, or online gradient descent. And there are different other names. If you look at the scikit-learn logistic regression optimizer, what's it called? The algorithm, maybe it's called. So the optimization algorithm have different versions. As far as I understand, they are different variations of gradient descent.
Got it.
Yeah.
Yeah, and I have another doubt. So I was just thinking, we are working on churn, let's say churn or customer defaulting. So it's basically we're using logistic regression to classify a target variable, but at the end it's binary. So what if we have what if there are multiple categories in our target category variable? So we use something called multiple logistic regression? Is there anything of that sort?
Great one. That's when, okay, so that's a case where the target variable is multi-class.
Yes, multi-class. Yeah, that's what I meant.
Typically referring to number of classes greater than 2. In that case, we won't use logistic regression then. You will learn exactly that in the neural network. So what happens is in the neural network, the data sets didn't change. I'm still using default as the example, and you'll still do the homework with the churn. But in that case, what we do is we will relax the assumption of binary target, but we will build a model to work with multi-class, even if it's a binary. So binary variable is really a special case of multi-class, right?
Yes, right.
So in that case, what's changing is instead of having only one output unit, you will have multiple output units. And each of the output unit is trying to classify or maximize the accuracy of that particular class.
Okay.
That makes sense?
Yes.
So in that case, it's no longer logistic regression then. It's neural network. You can still use the same activation function. The whole mechanism don't have to be changed, but there's a caveat. So that's why an improvement in that case, a multi-class implementation case, we will use softmax activation, which is a better version. Yeah.
Yep. Thank you so much, Professor.
Great questions. Any other questions? We barely used 20 minutes. No more? Somebody would like to sing a song?
Yeah, I have another question, Professor.
You want to sing a song?
No, the question. So you said, this might sound silly, but you said in order to handle high variance, we might have to reduce the complexity of the model. So what do you mean? What do you mean the reducing the complex? When you say reducing the complexity of the model, what do you mean? What should we reduce?
Yeah. So you're talking about high variance case. Yeah. So we typically say that the model is overfitted, right?
Right.
In terms of reducing the complexity of the model, it could be interpreted differently for business folks who are familiar with statistics, and for really machine learning people. Business people can be considered machine learning people if they understand how machine learning works, how machine learning is different from stats. Model complexity for statistics is like, the number of variables you include, or how many complex terms you introduce to the model. For in the regression framework, think about increasing a lot of interaction terms and a lot of squared or quadratic terms. That will really increase the complexity of the model. But that thinking is kind of flawed because it kind of sets up the mindset. The mindset is that the more variables, the more complex the model. It doesn't have to be. In the framework of machine learning, the complexity of the model comes in two ways. One is the type of model. Linear regression is less complex than neural network. That's for sure, because neural network has the ability to use nonlinear variations to make classification. It can become really complex and have a lot of nonlinear hyperplanes to detect the pattern. So the model is more powerful, it's more complex. When you compare different types of models, sometimes the comparison is quite clear, but you can't really compare models fairly, right? So a better sense of model complexity is within the same framework. How do you decrease or increase the complexity? For, let's say, for neural network that you have, one hidden layer and 10 hidden units in that layer, model complexity in a way is how large the weight is. When the model learns the weight in the learning process, some of the weight will be increased, but some other weights will be decreased. The model will learn what variables are making an impact or has a better correlation with target. Is more useful to predict the target. It will increase the size, positive or negative. It will increase the size of that coefficient, trying to capture that pattern. But for those variables that are not helpful in predicting the target, the model will decrease the size of the coefficient. So that's one sense. If all the weights are reduced to 0, you almost have a very simple model, right? Even though you have a complex structure of the neural network, but if all the weights are 0, then model is not complex at all, despite the structure. So that ties back to overfitting and high variance. A typical reason for high variance is overfitting, and overfitting is because the model is fitted to the training set without proper regularization, right? So the regularization part is to adjust the optimization process by allocate some penalty to the sides of the weights. You add in the L2 regularization, it will prevent the model from learning large sizes for the coefficient, because doing so really goes against the optimization process, right? Because the weights will take a square and it will be included in the cost. The model will, by nature, it will avoid learning weights that are too large. So in the end, regularization will push the model to further reduce the size of those coefficients that are really not making any impact in terms of predicting the outcome. And it will also help shrink those extremely large coefficients to help the model avoid, jacking up the weights just to make it right for those points in the training set. So I hope that's understandable.
Yes, sir. Yes.
Yeah.
Thank you very much.
Yeah, great. All right. Any other questions? No? Then we can say good night then. All right. Thank you. See you next time. I will end the meeting now.
Bye, Professor.
Huh?
I said bye, Professor.
Yeah, bye. Have a good night.